Okay, we'll start now. So hi everyone, I'm Greta Harrison. I'm a senior content developer here at California Dreams. Thank you so much for joining us for our latest technical seminar. Today we're pleased to be hosting Dr. Paul Juodawlkis. Paul is a principal staff member in the MIT Lincoln Laboratories Advanced Technology Division. In this role, he provides strategic guidance and technical expertise in the areas of program portfolio evolution, cross-cutting technology development, and partner relationships. During over 30 years at the laboratory, Paul has served in a variety of roles, including hardware systems engineer for airborne multi-sensor instrumentation system, photonics research scientist developing photonic analog to digital converters, and high-power semiconductor optical amplifiers. He was also a group leader, guiding teams developing electro-optic materials and devices, integrated photonics, lasers, and quantum-enabled processors and sensors. Paul is a fellow of the IEEE and Optica, and he's been an active volunteer in technical conferences and professional society leadership and advisory boards. He holds a BS from Michigan Technological University, an MS from Purdue University, and a PhD from Georgia Tech, all in electrical engineering. So thank you so much to Paul for joining us today, and over to you.
Great. Thank you, Greta. I'm very happy to be here. And I'd also like to thank AJ for inviting me to give this talk. So, as Greta mentioned, the title of the talk is From Physics to Field of Systems. And over the course of my career, I've actually gotten to live that, going all the way from doing airborne testbed work to developing, looking at new physics in semiconductor optical amplifiers and actually leading the quantum information group. I guess one thing is, so this is going to be a broad coverage of Lincoln Laboratory and the Advanced Technology Division. So, there might be some people that might spur some ideas, but he went through pretty fast through that. So I'd be happy to have follow-ups or actually point you to people who might know more about specific topics. So my email address is down here. So please feel free to reach out to me after the session. So with that, I'll jump in. Um, so Lincoln Laboratory. Lincoln Laboratory is a DOW federally funded research and development center, or FFRDC, that was founded back in 1951. So we're actually celebrating the 75th anniversary of our founding. And we're part of MIT. We're all MIT employees here, but we exist as a contract between MIT and the Air Force. It's an unfunded contract that gets renewed every 5 years. And so the main campus here is down on the MIT campus. Whereas Lincoln is located out on Hanscom Air Force Base. On campus, they focus primarily on education and basic research, where at Lincoln we do applied research and development, and we do a combination of unclassified and classified work out here at the laboratory. So Lincoln's origins, it has a long legacy associated with the MIT Radiation Laboratory, which, as some of you may know, developed radar during World War II. After the World War II was over, the radiation lab disbanded. But then in the early 50s, the nation just identified a big problem, is that the Soviet Union had strategic bombers and also nuclear weapons. And so they could come over the poles and get to come all the way to, say, Burlington, Vermont, before we would have even known they were coming. So they stood up Lincoln Laboratory, and the first project that Lincoln worked was on the semi-automatic ground environment, or SAGE system. That was a system to build air defenses and deploy them up in northern Canada. Lincoln played a roles as both system integrator and technology developer. I'll mention more of that in the next slide. The SAGE system was developed over 7 years, and then MITRE was spun off in 1958 to acquire systems. So I'm going to use this chart here to describe the way that we think about things at Lincoln and approach problems. And I guess it's really driven by the system analysis-led capabilities and technology development. So we typically start with a problem. And then it goes into a concept phase. We'll do some analysis, perform some testing, maybe some red teaming. So what could go wrong? How would the adversary deal with it? And then go into the concept again and kind of go through this cycle. After this analysis has gone through, we'll often do prototyping of a new system. And then we don't manufacture anything here at Lincoln. We just do prototypes and first of a kind. And if there's interest in having more of these, we'll hand this off to another contractor. We're working with industry to be able to do this. But if the technology isn't already available, sometimes we have to go off and do science and technology to develop the technology, do tech maturation, get it out into industry so that these systems can be prototyped and acquired. So Lincoln Laboratory really combines this system thinking with advanced technology R&D to solve these critical problems. And so as a first example, the one that I mentioned on the earlier slide, the problem was these Soviet nuclear-capable bombers. The proposed solution was the SAGE system, But in those days, there was a lot of technology that was missing from being able to enable the system. So Lincoln got involved in developing a variety of technologies, magnetic core memory to enable real-time computing, early modem technology for getting the information from the radar site to a site where they could then deploy the aircraft, and also things like pen interfaces as well. Um, After the technology was developed, there was a prototype built down on Cape Cod, and a few other sites as well that sort of verified that the technology worked. And then MITRE was spun out of Lincoln Laboratory to acquire and deploy these systems. And so this led to the deployment of the SAGE system. And so, MITRE's gone off to do a lot of other things, and so has Lincoln after this first project. So another interesting project that was kind of going on about the same time, maybe 10 years after Lincoln's founding, was a lot of early work on semiconductor optoelectronic materials, and some materials like gallium arsenide. And so here's a team of folks here: Bob Keys, Ted Quist, and Bob Redeker, who developed early gallium arsenide LEDs. And as soon as they had those LEDs, they then started doing field experiments with them. So they put a gallium arsenide LED in a cryo-cooled telescope, and they put it up on top of Lincoln Laboratory, and they pointed it out at Mount Wachusett, where they had a searchlight aperture with a photomultiplier tube there, and then they transmitted television patterns. And so for those of you who might remember, we're old enough to remember, these were the sort of the television patterns that get broadcast at night after the television stations would get shut down. So I know that this was done at night. And because during the daytime, the same group of folks were also developing some of the first, diode lasers. They were doing field work at the same time as doing advanced technology development as well too. And so a few years ago, I led an effort to engage with folks from General Electric and IBM and have all three organizations recognized with an IEEE milestone for the initial demonstrations of the semiconductor laser that took place in the fall of 1962. So Lincoln, started this optical communications work back in the early 60s, and it's been going on through these days to today. And here's a nice example of a graphic that was taken off the NASA website of a number of different free space optical communication missions that they've had over the past decade, so 2014 and 2026. And Lincoln Laboratory was involved in all these projects developing payloads. So, for example, if you watched the recent Artemis mission and saw those really nice high definition videos coming back, that was partially due to a payload that Lincoln developed and deployed on that test bed. So Lincoln got that start way back in the 60s and has been carrying through to this day. So Lincoln Laboratory today, as I mentioned, we're out on Hanscom Air Force Base. There's a number of new buildings that have popped up over the years, but we still have some of these old 1950s buildings that were built in the early days. We have a number of other field sites. We have a space surveillance site with a number of radars out in Westford, Massachusetts. We also help out on out in Kwajalein Atoll at the Reagan test site, where we do look at reentry vehicles as well as space surveillance. A couple of other field sites were out in Nevada and New Mexico. The images down here represent the different mission areas of the laboratory. Some of them are the same as they always have been. Air and missile defense goes way back to those early days. Soon after that, we got involved with space systems. Actually, the Millstone Hill radar was one of the first radars to track Sputnik when the Soviets put that up in 1957. And then soon after that, we got involved with both RF and optical communications. And over the years, as the challenges to the nation have evolved, we've added new areas such as homeland protection after September 11th, cybersecurity, as that's gotten to be a bigger threat, as well as our most recent division, the Biotechnology and Human Systems Division. We have an engineering division that helps us, that bends metal, helps us do analyses, and also does things like environmental testing for airborne, ship-based as well as space-based prototyping. So the lab has about a annual revenue last year about 1.45 billion. Of that, 50 million of it comes off of a congressional line item for Lincoln Laboratory, about $40 million there, and the rest of it comes in through different program activities, working with the sponsors and bringing in funding. About 4,500 employees, and a very large number of different programs that are going on simultaneously. What I'm going to talk about next is the Advanced Technology Division, which is the division where um, I've been residing for the past 27 years or so. So the Advanced Technology Division, at the technology level, we're developing a number of different sort of products or technology areas, ranging from integrated photonics, integrated RF and photonics, lasers, advanced computing, imagers, materials and microsystems, and quantum computing. And the idea is to develop these components or subsystems that make their way up into the system mission areas at the laboratory and in the government. So it might be developing a new laser for undersea communications or a new imager for optical surveillance. So trying to focus on this materials, device, and subsystem level to enable new types of systems. And to be able to do this, we have a wide range of core competencies, so experts in all of these different areas, but then also a lot of facilities to do everything from quantum sciences to optics and optical devices, integrated photonics and packaging. And throughout the rest of the talk, I'll be showing some highlights of all these different competencies that we have at the laboratory. So here's just some of our electronic photonic fabrication resources. Our primary facility is our Microelectronics laboratory, which is a 200 millimeter silicon fab tool set with 90 nanometer lithography. It's a very flexible facility where we can do a wide range of things from CMOS and silicon photonics, advanced imagers, superconducting electronics. We also do wafer-scale 3D integration in this facility, and we do a variety of multi-project wafer runs. In addition, so this is primarily a silicon facility. We also have a compound semiconductor and diamond capabilities as well too. So we grow compound semiconductors in a variety of MOCVD and MBE reactors. We have a separate 3.5 fabrication clean room for processing those devices, for doing things like optoelectronic components, RF, and 3.5 photonic integration. And then we have a lot of packaging facilities and back end of line. So for like flip chip packaging, wire bonding, reliability and lifetime testing, and then also hybrid integration. So a lot of physical resources for doing fabrication of electronics and photonics. And as an advertisement, we have a new building that's currently being built. I actually just walked by this today. The groundbreaking took place in July of 2022, and they're estimating right now that the building is going to be completed in January of 2028. So a little bit less than 2 years. We're already starting the planning about how we're going to move all the tools from. It's about 50 different laboratory rooms around the laboratory are going to move into this new facility. This was paid for by military construction funding, and it's just this way to be able to consolidate our compound semiconductor and packaging facilities. So we're very excited about this. And then these next 3 slides, I just have a laundry list and some photographs of all the different tools in the facilities. So our microelectronics lab, our compound semiconductor, we have all these lithography, etch tools, deposition materials, grills. So I'm not going to go through the details here, but you can find more details if you just go to our website, www.ll.mit.edu/MPF. You'll be able to get all this information that I'm presenting. But so fabrication capabilities, prototyping capabilities, CMOS, integrated photonics, imagers, superconducting digital logic, as well as superconducting qubits, trapped ion circuits, and then things like avalanche photodiode arrays, GaN on silicon CMOS, microhydraulic actuator. So a wide range of different prototyping capabilities. And then also, as I mentioned, we have a lot of packaging facilities, both for electronics and optics, that we can leverage and partner with folks outside of the laboratory and make available to the community. So please, if you want more information on this, either reach out to me and I can connect you with the people that have information about this, or I can answer questions as well. Okay, so that's just a high-level view of the Advanced Technology Division. Now what I'd like to do is to go into some of the details of each of the groups. So first, we'll start off with the Advanced Imager Group. So this group does a range of things involving developing detector arrays, so things like charge-coupled devices or CCDs, Geiger-mode avalanche photodiodes that are capable of detecting single photons, as well as single photon detecting superconducting detectors. In addition to developing the detector arrays, They also build the readout circuits that are needed to be able to interface these focal planes to the outside world. So one of the areas they've developed are digital focal plane arrays. I'll talk a little bit about that on the next slide, as well as reconfigurable imagers. And they also get involved, either within the group or then they partner with other groups here at the laboratory or outside to developing new imaging and sensing applications, both for scientific and DoD or DoW capabilities. So one novel technology that Lincoln developed over the past couple of decades is something called our digital focal plane array, or DFPA technology. And here, what I'm going to do is I'm going to compare with a traditional analog pixel. So you have your analog detector that's detecting photons and converting those into electrons from some scene you're imaging. Those are then collected on a capacitor. So you're charging up this capacitor over time, and then you have analog switches that are reading out the individual pixels. The DFPA, so it typically uses a fairly large capacitor to be able to do this, but what will happen is often is this, if you have too many photons coming in, it will saturate, and so it kind of will limit your dynamic range. What the DFPA does, it's got a much smaller capacitor. Each time that capacitor charges, it increases a count in a counter, and then just resets and goes through. So what you can do is it's sort of like an infinite size capacitor that allows you just to keep integrated. And so you can also do things like shifting data around on the focal plane. You can do additions and subtractions. You can actually do processing on the focal plane by having this DFPA approach. So really, it enabled some new capabilities. And so just to highlight some of those, it does increase the dynamic range because your capacitor never completely fills up. You just keep as long as you have enough bits in your counter. You can do temporal filtering by adding and subtracting things. You can actually see things in time. You can do spatial filters, image stabilization, and then time delay integration for scanning mode imagery. So this technology was developed at the lab for a number of years, and then it was spun out to a company called Copious Imaging, which has been since bought by Anduril. And so the technology has been transferred out of the laboratory and is being done out there. So, okay, so that was the imager group. We also have a laser group. And so if you can imagine combining some of those really exquisite single photon detectors from the imager group with pulsed lasers from the laser group, you can enable laser radar or LiDAR systems. And so for those of you not familiar, the way a LiDAR system works is you take a pulse laser, and typically this is a neodymium YAG microchip laser, produces short pulses on some periodic basis. That those laser pulses go out through an optical aperture, are reflected down, here in this case, down toward the ground. Those photons come back up off the ground through the system and are then imaged on a focal plane array of Geiger-mode avalanche photodiodes, which act as timers. So you send the pulse out, you turn timers on behind each of these Geiger-mode APD pixels, and then on a pixel-by-pixel basis, you're measuring the time of flight of those photons coming from the platform, this airborne platform, to the ground and back. And so that gives you sort of the distance down to the ground. If you combine that information with GPS, IMU, and do signal processing, you can create these very nice 3D maps from this airborne platform. And I'll give you an example of that on the next slide. So here's some example 3D LiDAR imagery that was taken over Boston by a sensor called the Machete system. This was taken back in 2014. And so our advanced technology division, we developed the lasers and the Geiger-mode avalanche photodiode arrays and the readout circuits, and then we handed them off to folks in our active optical systems group, who then integrated these on an aircraft and then flew these missions. And so this was taken 6 passes over Boston. Each pass about a minute long, so a total of about 360 seconds worth of data. The plane was up at 14,000 feet. I think that, so the laser wavelength was about 1 micron. And one of the interesting things is you can just kind of see, you can actually fly through the Zakim Bridge there. You can see here on the USS Constitution, you can see some very fine, some of the ropes and guides around there, and just various things so it really gives you this very exquisite, it's mapping about 9 square kilometers with about 10 centimeter voxels. So very interesting capability to be able to do 3D ground mapping. We've applied that in a variety of ways. One of the first ones, we built a system. What we did is our active sensing group built a system called ALERT, Airborne Laser Imaging Research Testbed. They flew that locally here, and then they transitioned that over to the National Geospatial Intelligence Agency and the Air Force, who then flew this over Afghanistan. So a large number of flights, almost 1,000 flights, 4,700 hours, and mapped a large portion of Afghanistan, making Afghanistan one of the probably least mapped countries to the most mapped. And this was obviously, as you can imagine, from a Department of War, military exercises. It was a very important thing for the nation for this to be able to do. So this is an example of taking those basic technologies, the lasers and the photodetectors, integrating them in the systems, doing this initial prototyping, then handing it off to the government to be able to apply the technology. Another area where that's been used in a couple of different cases was for disaster recovery. And so in 2017, when Hurricane Harvey came ashore, it really did a lot of damage from the winds and the flooding and everything like that. And so FEMA asked Lincoln Laboratory to bring one of the systems down there. This was the Airborne Optical Test Bed, and doing wide area maps, debris analysis, flooding maps, and infrastructure assessment. So using this LiDAR technology really gives disaster recovery people another way to look at very large areas and kind of get an assessment of where the damage is and how they can actually route recovery capabilities there. Okay, so that's all I have to say about imagers and lasers. Let's switch on now to materials and microsystems. So the areas that the advanced materials and microsystems groups work on are materials by design, wafer-scale systems and technologies, flexible systems and technologies, and then also smart fibers and textiles. And I have slides on each of these topics in the next few slides. So Lincoln does have CMOS capability. As I mentioned, we have a 90 nanometer capability using 193 nanometer lithography. And while that is far from sort of the most advanced node, you could still do a lot of useful things with 90 nanometers. So we have different flavors of that. We have cryogenic CMOS, low power, high voltage, RF areas. We also have a rad hard version as well too. And we have a fairly developed process design kit, library and IP. We can do simulation and process development, and then fabrication and testing as well too. On the materials side, we've been developing an approach that we call machine learning enabled materials engineering, or MEAM. And this is really just a way to more rapidly discover materials by applying machine learning tools. So, the idea about here doing some, initial simulations of different types of, different modeling to be able to, ML modeling to be able to come up with what the best path forward is, and then doing some high throughput synthesis and then high throughput characterization to really accelerate this, coming up with next ideas to doing some fabrication, to doing some testing, so that we can really, developing, experimentally validated materials in small quantities within a sort of a year time frame, really reducing the amount of time to develop new materials. And we're applying this across a variety of materials areas. Another interesting capability is something we call our Defense Fabric Discovery Center, or DFDC. And this is a partnership between the AFOA Manufacturing USA Institute, the Commonwealth of Massachusetts, and also the Army, and also other sponsors have gotten involved. And this is just a fairly unique capability, both for doing very custom silica fibers, so dope fibers, photonic crystal fibers, as well as a lot of non-silicon fibers. We do polymer fibers and actually embed electronics in them. So we can do things like we can pull polymer fibers and embed electronics and wires in them, or we also have draw towers for the silica fibers, and we can weave these into textiles, and then doing simulations of these and doing computer-aided design, and then we also do systems integration as well. So this is just a slide that covers the broad range of these capabilities in different areas: sensing, comms and computing, and health protection, and just applying this, embedding electronics and capabilities in the fiber. So doing things like, flexible fabric antennas, or making very small devices that can then be woven into clothes for certain applications. I guess another thing in terms of flexible, there's also some really nice work going on flexible printed circuit boards as well too. Okay, and switching gears now to the integrated RF and photonics group. Their three pillars are novel RF apertures, RF digital convergence, and integrated photonics. So under the RF apertures, they're doing a lot of work on wideband sensing systems, panel-based phased arrays, which I'll go into more detail on, and also small sat antennas. In the digital RF convergence, a lot of work on simultaneous transmit and receive, multifunction arrays, and then distributed RF processing. And I'll go into a lot of detail on the integrated photonics, since that was one of the areas that I've been helping build over the past couple of decades. So one of the areas that the group got into was, the problem that was posed to them was the FAA and NOAA have a large number of radars out there that are really getting old. They're sort of reaching their end of life. There's a lot of high operation and maintenance costs, and they're all different. They're complex, and so you have to each of them, the maintenance for each of them is different. So there's 510 different radars, 8 radar types, and so that was a big challenge in terms of the cost and being able to keep these up to state to keep for monitoring weather and air traffic. And so Lincoln got involved in this, and this is that a system analysis approach that I was mentioning earlier. So the issues were production costs and end of life device systems, and how do you deal with that? So there was a typical slat architecture that was used for phased arrays, and so Lincoln's been developing a tile-based architecture. The technology did not exist, so we had to go off and be developing and maturing the technology. We then did a prototype of this antenna, which was then transitioned out to the NOAA National Severe Storms Laboratory out in Norman, Oklahoma, back I think about 7, 8 years ago time frame now. And this has been out there taking a lot of data. And so now Lincoln's done this initial prototype, and now the FAA and NOAA are working to build more of these to replace that aging infrastructure. And so along the way from that, we also had to develop some advanced technologies. So things like gallium nitride on silicon, RF processes, wafer level 3D integrated GaN on silicon with SOI CMOS, as well as microjet thermal management. So here the idea is actually putting microjet cooling, liquid cooling on the backside of silicon wafers, directly integrating with the devices to provide cooling for these high power devices. Okay, so changing frequencies is significantly going from the gigahertz range up into the hundreds of terahertz. Let's talk about integrated photonics. So here's the spectrum going from a tenth of a micron out to 1,000 microns. And most of the work going on in fiber telecom and datacom is kind of between the sort of 1.2 to 1.6 micron wavelength range. However, there's a lot of other applications at wavelengths beyond that. So down at the short wavelengths, you have all the atomic transitions for quantum sensing and computing, biosensing, underwater communications. You really have to be down in the blue-green wavelengths there. To longer wavelengths like IR countermeasures and terahertz imaging. So a lot of the infrastructure that's been applied for fiber datacom is silicon fabrication resources. So leveraging the CMOS industry, so using silicon for guiding and modulating the light. And then adding germanium into the platforms for doing the detection, sort of in this wavelength range here, this 1.2 to 1.6. However, if you wanted to go down into the visible wavelengths, silicon becomes a very good absorber, and so you can't go down there. So we work a lot with other materials like silicon nitride or alumina to be able to get down to the other wavelengths as well. We also like silicon nitride because it will handle higher power and has lower loss than the silicon waveguides as well too. Another thing is that some applications require modulators that are better than silicon modulators. So we've been doing a lot of work on thin film lithium niobate. There's a lot of interest and activity in this area for datacom, but then also we think it's the appropriate material for microwave photonics, and I'll talk a little bit about that. So these materials are all great at modulating, guiding, detecting light, but you also need compound semiconductors to serve as the light generation. So for lasers, such as gallium nitride down at the short wavelengths, gallium arsenide, indium phosphide, and then going out to the long wavelengths, quantum cascade lasers. So, really the applications of interest to cover this full wavelength range, you really need a range of materials, and integration processes. And so, as I mentioned, so Lincoln is primarily a systems house, and so we always have this system motivator out there to think about how we can develop new technologies to solve system problems. And so, a lot of times we'll be working with our system partners, and they'll come up with device requirements. I need a new laser that does this, or I need a new detector that does that, or a photonic integrated circuit. And so the idea is that when we develop this technology, it can then solve those system level problems. And so here at Lincoln, we have this is common for probably everybody, but we have this vertically integrated development cycle. So we'll take these design requirements, go into design phase. Maybe we need to develop new materials, compound semiconductor materials, or some, perhaps germanium or silicon. Then we do the fabrication, packaging, testing, and assessment. And if the device that goes through the cycle works, we'll hand it off to the system folks. If it doesn't, then we turn this cycle again. And by having these vertically integrated resources, having all the capability to do design and simulation, mask layout, fab process design, growing the materials, fabricating in our silicon facilities or our compound semiconductor, doing this flip chip integration, doing electronic photonic integration, fiber to chip bonding, and then also testing. Having that all under one roof allows us to turn that cycle on. It's expensive to do that, but it also allows us to really rapidly to prototype these new materials and devices. Not to say that we do everything internally. Sometimes we'll go out and buy epi outside, or we'll partner with someone for packaging or testing, but we do have a lot of capabilities under the one roof here at Lincoln. And so the different technologies that the photonics team has developed over the years are sort of based on silicon foundry. So we do have a silicon photonics process, and we do apply that sometimes for special cases. But if you just want like standard silicon photonics, we typically would direct you to something like AIM Photonics or Global Foundries or Tower Semiconductor. But what we do is we're trying to do things a little more special. So we do a lot of work on silicon nitride and alumina for going to those visible wavelengths, and also lower loss, higher power. We do have a ultra low loss waveguide, sort of a tenth of a dB per meter. To go out to the midwave IR, we've developed germanium waveguides, and we've also done some work in optomechanics. On the compound semiconductor side, we have watt class emitters, wideband photodetectors, and then we can bring these together in hybrid and heterogeneous integration through flip chip bonding, bonding material at the wafer level, either 3,5 or lithium niobate. And we've also done some work on heteroepitaxial growth of 3,5 on silicon. And the three main pillars for the integrated photonics area are what we call quantum interfaces, microwave photonics, and then another bucket, sort of just like lasers, LiDAR, and optical comp, everything that doesn't fall into those two categories. And so we partner with a lot of folks on our quantum interfaces. We work with folks in our quantum sensing group to develop laser beam delivery and control for trapped ions, both for quantum computing applications as well as optical atomic clocks. We also partner with folks in our communications division to make photonics an interface to Diamond for doing quantum repeaters. I'll get into some more details about the microwave photonics, but we have a wide range of activities to make integrated microwave photonic circuits. And then on lasers, we do work on developing high energy lasers, as well as a project that was really fun, gas mapping LiDARs. We work with a small company called Bridger Photonics. So really vertically integrated resources from the UV to the midwave IR. And so one platform that we've been developing over the past decade, we call a photonic multi-chip module platform. And it really comprises we use silicon nitride, primarily for the waveguides for this platform, also alumina, but we can also add silicon waveguides, and we've done chips where we can couple from the silicon waveguide into the silicon nitride waveguide. We had high-speed electrodes and hybrid integration structures so that we can then flip chip on 3.5 photodiodes or 3.5 optical amplifiers that can then create lasers and photodetection on chip. We also bond thin film materials, either compound semiconductors. We also bond thin film lithium niobate, both for making high-speed, high-performance electro-optic modulators, as well as periodically poled Piplin type devices for doing frequency shifting. And then also electronics, we can do things at the chip scale, or a lot of the work we're doing right now is just wire bonding these off to a board. But we can also do wafer scale integration as well too. And so one thing we've demonstrated over the past few years using this platform is a millimeter wave receiver on chip. So we had this vision of implementing a full millimeter wave receiver on chip, and we developed all the components to do that. So the thin film lithium niobate modulators, high power external cavity lasers, photodiodes, as well as the silicon nitride waveguides for routing the light, and also implementing very nice tunable optical filters. So we developed all the components, and then we also integrated all these components to realize this receiver on chip. So this chip has a laser. So this is a high power optical amplifier, a slab coupled optical waveguide amplifier with an external cavity. It has a pair of thin film lithium niobate modulators. It's got some optical filters and then balanced photodetectors on the back end. So what you can do here is you can actually bring in a millimeter wave signal into one of the electrodes, bring in a millimeter wave local oscillator, offset frequency from this millimeter wave signal, and then you then filter these signals and beat them in the photodiode and generate an IF output. So if I bring in 40 gigahertz or 40 gigahertz RF, 39 gigahertz LO, I'll get out 1 gigahertz of IF at the output. So we're very excited about this, and we continue to be pushing and developing this technology. Okay, so that's all I have to say about integrated RF and photonics. Now I'm going to wrap this up with the last group that I haven't talked about, our advanced computing and quantum computing group. Both of those are with one group. It's really based on superconducting electronics for both of those technologies. So this is really their three pillars are quantum information science. So they have a quantum theory group where they're looking at trying to identify quantum utility for both the DoD and commercial sector. Looking at mapping algorithms to processors, and also looking at different physical qubits. In the superconducting qubit area, they're really developing new qubits, starting to scale these into small scale circuits to start evaluating their activity. And we also have a research foundry called the Squill Foundry that I'll talk about in the next slide. And then also we have superconducting electronics. So using superconducting technologies, not for doing quantum, but for doing high speed digital signal processing at lower powers that you can get compared to CMOS electronics. So I think I mentioned in the superconducting qubits, they're doing novel qubits, materials investigations, scaling up number of qubits to do test beds. They make some very nice quantum limited amplifiers called traveling wave parametric amplifiers and provide these out to the community. And then, looking at 3D integration, so doing basically stacking things up to be able to make really high performance qubits. And then also the Squill Foundry, which I'll talk about on the next slide. So here with the Squill Foundry, we have one sponsor who is funding us over a 5-year period to allow academic groups and some industry groups, I think some government organizations as well, to design into our superconducting qubit process. And then we do multi-project wafer runs, dice the chips off, and hand them off to the different users who are accessing the foundry. And then we have interactions with those users, and then once a year we get together for a large symposium here at the laboratory to discuss the results. And so it's been a very successful process, and I think they're in maybe year 2 of the 5 years right now. But it's a way of, so that a lot of academic groups, they might be a small group, and this, instead of having everybody to reinvent the wheel and build their own qubit, fabricate their own qubits, this allows it to sort of accelerate what we can do by leveraging Lincoln's resources and getting the qubits out there to people. And then on the superconducting electronics side, we have the most advanced superconducting electronic process called our SFQ5EE node that's available in an open process. So it's been developed over a number of years. We do multi-chip module capabilities of this, looking at signal processing, superconducting computation, and then we also do readout integrated circuits for superconducting detectors. And one of the motivations here that I've alluded to is trying to apply superconducting electronics to supercomputing. And if you go ahead and look at the energy savings from this SFQ-based electronics, even if you have to cool this down to 4 Kelvin to be able to get the superconducting capability, even when you include the cooling power, the calculations show that there's 100x power reduction and sort of 140 billion of cost savings from using less electrical power by utilizing superconducting electronics. And there's a couple of startup companies that are out there right now. And so Lincoln is engaged with them, but do really try to develop and try to learn how to develop this technology and then transfer it out there to try and see if this is really a viable concept. Okay, so that is an overview of, world overview of the Advanced Technology Division. And so why does this division exist? It's kind of part of Lincoln Laboratories' advanced technology role. So this is a Defense Department of Defense plan for administration of MIT Lincoln Laboratory. And it's really, one of the Lincoln's roles is to carry out this program of research development, pertinent national defense with a particular emphasis on advanced electronics. So where we sit in the whole community is somewhere between university research and foundry processes. And so here, what we can do is between our compound semiconductor laboratory capability and our microelectronics, we can do things that have more maturity, more devices, but also still have a lot of flexibility. In our microelectronics lab, maybe there's less flexibility, more higher capabilities, ISO 9001 certified. In our CSL MIF, we have we have more capabilities, more materials can be brought in there and stuff like that. So it's a little more researchy, a little more, but we can really span this range here between these areas. And we also collaborate heavily with MIT with Dot Nano down on the MIT campus as well for even more basic research. Okay, so next couple slides talk about some ways to engage with us. So there's a number of different models that we have. One would be use some fabrication tools. So you bring the IP and we supply the fabrication tools. So you basically you can get access to be able to have technicians or engineers be able to come in here and kind of use the capabilities that we have in-house here. Another one would be design into the Lincoln Laboratory processes. So you bring the designs, we'll fabricate them in our process. We have PDKs for a number of the technologies. We can also do multi-project wafer runs. Designing into our packaging and test capabilities, or leveraging our materials analysis capabilities as well too, which is an emerging area. And the third one would be engage in collaborative development, work together to develop a new process or device or subsystem. So we come together. There's ways, depending on how we do it, that we could have joint IP, or you bring your IP and we bring ours, and then what's done jointly becomes joint IP. And we agree to that IP is done up front. So we can, there's a wide range of ways to do this: direct government directed programs, collaborative agreements, cooperative research and development agreements, and test agreements as well too. So we're very open to this, and we have engagements with folks throughout academia, government, and industry. And so we are pretty heavily involved in the Microelectronics Commons. Our primary hub is the Northeast Microelectronics Coalition, or NEMC hub. And in the round one of the ME Commons, we were involved in 4 major projects. One involving aluminum gallium nitride devices. The lead was analog devices. Another one was Sivers semiconductors, and here we were developing simultaneous transmit and receive phased arrays. We were involved with some quantum photonics in a project called CHICP. The lead there was BAE. And here, this was really for developing photonic integrated circuits for quantum sensors. And then another one with the UC Berkeley hub, the Northwest AI hub, where UC Berkeley was a lead, and this was developing ferroelectric FETs. So some of these have gone on to the second round. Some of these did not make it out of the first round, but. And we do have things coming up. We're promoting the proposal submissions for round 2. We're a team member on 6 proposals, and proposals are coming from 5 different hubs. And then also we're involved with some of these NEMC Hub Awards. It's a project called Propel, Powering Regional Opportunities for Prototyping Microelectronics. And so we're the fabrication partner on 3 company awards for that. And then we also, through a different NEMC grant, we have a project under their SCALE program. And this is to procure and facilitate a couple of reactors from Axtron. These are both 300 millimeter reactors, one focused on gallium nitride and another one on 2D materials. Axtron had a very strong interest in getting these tools into the U.S. I think it's my understanding that the U.S. that there's not a similar tool in the U.S. right now, and so we'll be having Axtron engineers on site and partnering with internal external partners to be leveraging these capabilities. Okay. And so I'm at the summary here. Lincoln, as I mentioned, Lincoln has this long history of developing and transitioning advanced technology and prototype systems. We have this integrated approach going from system analysis to prototyping, and then when needed, doing the S&T to develop these advanced technologies. The division that I sit in, the advanced technology, also here at Lincoln called Division 8, leverages this core set of competencies to develop materials, devices, and subsystems that we get out into critical systems. And we're always interested in developing and enhancing partnerships with industry, academia, and government. And so I'd like to use this as just an opportunity to open the discussion and find ways that we can partner with you. So I'll end. Thanks.